All right, today we are diving into a paper that proposes something, well, something pretty radical. It's a theoretical framework for fighting cancer not by poisoning it, but by, get this, building a physical cage around it. Okay, let's get into it.
And that right there is the question at the heart of this whole thing. For decades, our main approach to cancer has basically been chemical warfare. But this idea, it just flips the entire script. It asks us to stop thinking about finding better poisons and start thinking like construction engineers.
So to really get why this is such a huge deal, we first have to talk about the fundamental problem with pretty much all of our current cancer therapies. It all comes down to a really tricky balancing act.
It's called the therapeutic window, and it's this incredibly narrow tightrope that doctors and patients have to walk every single day. For years, so much of nanomedicine has been about one thing. How do we make this window just a little bit wider? How do we deliver the poison more precisely? But the poison itself was always part of the deal.
And that's the key thing to remember here. In classic nanomedicine, a nanoparticle is basically just a very, very sophisticated delivery truck for a toxic cargo. Its whole job is to get the chemo to the tumor, drop it off, and then its part of the story is over. The therapy itself is still just pharmacology.
So what if we just reimagined that whole process from the ground up? What if the delivery truck is the therapy? This is where the paper proposes a massive, and I mean massive, paradigm shift.
And here it is, the core concept. It's called total structural and metabolic isolation, or TSMI for short. The idea is you inject a swarm of nanodrones that don't carry any drugs at all. Nope. Their only job is to find the tumor and work together to build what the paper calls a carbon sarcophagus, a physical cage that completely walls off the tumor, starving it of blood, nutrients, everything it needs to live. It's death by deprivation, not by chemistry. Now take a look at this chart. This is where you really see what a big deal this is. When you stack TSMI up against other approaches, it's the only one that can check all the boxes. It's drug-free, it's resistance-proof, and it offers total isolation. This isn't just a small step up. The paper makes the case that this is a whole new category of treatment, a categorical leap forward.
All right, so how on earth would you actually build a cage inside the human body? I mean, it sounds like pure science fiction, right? But the paper actually lays out a super detailed 5-step blueprint that's all grounded in real-world physics and material science.
So the paper breaks this whole challenge down into 5 core technical hurdles that need to be cleared. First, there's a 2-key security system to make sure the drones only activate where they're supposed to. Second, they use something called quorum sensing, so the swarm knows when to start building. Third, the cage itself is a shock-absorbing lattice, a really smart material. Fourth is fluid flow analysis to help them navigate. And finally, there's a cleanup and demolition phase for getting rid of it all safely. We're going to touch on a couple of the most crucial ones now.
First up, the safety system. This is absolutely critical. You obviously don't want this cage getting built around your healthy organs. So the nanodrones have a dual trigger. They need 2 keys to turn on. They have to detect both the high acidity you find around tumors and a very specific protein on the surface of the cancer cells. This is a huge deal because it slashes the odds of a false positive. Other inflamed tissues might be acidic, sure, but they won't have that specific cancer protein.
Okay, next up, the building material. This stuff has to be incredibly smart. You can't just build a rigid, brittle wall inside a pulsing, flowing blood vessel. It would just shatter. So the paper proposes using what's called a thixotropic lattice.
And honestly, the best way to think about this is ketchup. Seriously, ketchup is pretty solid-like when it's just sitting in the bottle, but as soon as you apply force, shake it or smack it, it starts to flow. This proposed lattice would do the exact same thing. It would flex and give under the pressure of a heartbeat, then instantly snap back to its strong, solid state. That's how it could survive the constant mechanical stress inside our bodies.
Now, I know exactly what you're thinking. This all sounds amazing, but it also sounds incredibly futuristic. Maybe a little too good to be true. Well, the researchers knew you'd think that, so the paper directly takes on all the tough questions head-on. Let's run the gauntlet.
So, the first and most obvious question, the elephant in the room, is probably the one you're thinking right now. This is all just theory, isn't it? Where are the experiments? Where's the lab data?
And the answer is, yeah, it is a theory paper. And the author is completely, refreshingly upfront about that. The whole point of this work wasn't to build it in a lab, yet. It was to do all the heavy lifting on the math, the physics, and the computer modeling to prove that it could work in principle.
Think of it as a computationally validated blueprint to guide the people who will eventually try to build this for real. Okay, next question. Safety. These nanodrones are about 100 nanometers wide. That's way too big to get filtered out by your kidneys. So, wouldn't they just build up in your body and clog everything up?
Actually, that's a feature, not a bug. They're designed to be that big on purpose so they don't get accidentally flushed out of your system before they have time to build the cage. The really clever part is that the whole system has a built-in exit strategy. The cage is engineered to degrade over about 60 days, breaking down into tiny little pieces, smaller than 8 nanometers, that are then small enough to be safely cleared by the kidneys.
So let's just be crystal clear about this. It's really important to separate what this paper claims to have proven on a computer versus what still needs to be built and tested in a wet lab.
This table lays it all out really nicely. The paper provides solid computational proof that the drones can assemble the way they're supposed to and that the cage would be stable under the forces you'd find in tiny blood vessels. It makes a really sound theoretical case for that two-key safety system. But, and this is the important part, it explicitly does not claim that this system will kill a tumor in a living thing. That is the critical next step, and that part requires real lab validation.
And all of this leads to this one quote from the paper that just perfectly summarizes the ultimate goal here. If this works, it just fundamentally changes the rules of the game. It gets rid of the whole therapeutic window problem, it sidesteps drug resistance completely, it shifts the fight against cancer from a problem of chemistry to a problem of physics.
Which leaves us with a final, kind of mind-blowing thought. Yes, this paper is a blueprint, but it's a blueprint for a future where we might not just medicate diseases, but where we might physically build solutions to them, one nanodrone at a time. So, are we on the verge of treating disease not with chemistry, but with construction? It's a pretty powerful question to think about.